recording here, and then I'll tell you what the deal is. All right, so that's it, right? We're going to try to make things as simple as possible. Physics can get very, very complicated very, very quick, but it really boils down to these simple concepts. We have units that we take measurements with, 3 units, and we understand that the world is governed by 4 forces, okay? So here we go. These are our basic quantities and forces. We measure things in units of time, length, and mass. And all interactions between matter and energy in the world are governed by 4 forces. So think about that. Everything that you've ever experienced, every matter energy interaction in the entire universe is one of these 4 forces. Okay? We have gravity, weak nuclear forces, electromagnetism, and strong nuclear forces. And I will go into each of these as we go through this. But that's it, right? Sounds pretty simple. We have 7 different things we have to understand. 4 forces, 3 units. So let's go ahead and talk about each of these separately. First are our units of measure, okay? Remember time, distance, and mass, right? Time is based on the second, okay? So then you have to know, like, how long does a second last, right? And so how do we measure time usually? Yeah, but like, how do I know when 1 second has passed? Yeah, yeah. Clocks measure time, right? So time is measured by clocks. Well, what does a clock do, right? A clock just repeats the same thing over and over again, right? It has a little, for example, an analog clock has a second hand that ticks, right? Every time you get a tick, 1 second has passed, right? There's a bunch of gears, or there's a quartz crystal inside of that thing that's controlling how fast that ticking is happening, right? And the idea is that we're able to measure time with clocks. Now, clocks like the one on my wrist right now, powered by a battery, right? It has a little quartz crystal. That little quartz crystal vibrates, and a certain number of those little vibrations of the quartz crystal happens over 1 second. And number of vibrations happens inside the quartz crystal, and it makes the gears in my watch click that thing over 1 time. 1 second has passed, okay? The second is based on, for us, something very, very reliable. Now, clocks measure time, right? Clocks repeat the same thing over and over and over again. Well, atoms do this too. Atoms vibrate, okay? And atoms vibrate in a very specific way. They vibrate a specific number of times over a given length of time. So we found an atom called cesium, okay? And we learned, we learned how many times cesium atoms vibrate in 1 minute, in 1 second, okay? So now we say every time an atom of cesium vibrates this many times, we call that 1 second, all right? Have you guys heard of atomic clocks? Okay, well, so in you know how your phone keeps really good time, right? Keeps like really accurate time? Well, several times per day, all of our phones are sending a signal to the United States Atomic Clock Center, okay? And that atomic clock center is sending back a signal to our phone of what time it is, okay? Allowing us to keep a very accurate measure of what time it is. All of our phone, like, turn your phone on right now. What time does it say? 10:44. 9:44, right? And all of our phones are going to say 9:44 as long as they're hooked up to that atomic clock, right? If you're wearing a watch like I am that's not a smartwatch, not connected to that, right? My watch is going to say whatever time that I've set it to, right? If I've got like one of those automatic watches that I have to like keep moving my wrist to make it work, right? It's going to change time. It's not going to keep time as accurately, yeah? Yeah. So the most expensive watches, the Rolexes and all those very, very expensive automatic watches, they keep time way worse than the cheaper Casio digital watches, right? That's a separate talk. But the idea is that we have in the country, it's actually in Colorado, there is a center, place where people are, and they have these atomic clocks, and these atomic clocks keep the time for the entire country and other areas. Those atomic clocks use atoms of a material called cesium that we know how many times it vibrates, so that they can track every time cesium vibrates this many times, 1 second has passed. Okay, and we're able to keep very, very accurate time in that way. So the second is now based on the number of times an atom of cesium vibrates. Somewhere, somehow, someday, sometime, I've got that number written down somewhere on my computer. It doesn't matter for you how many times. It's billions of times per second, okay? But don't worry about the exact number, but there is an exact number. Someone knows it. It's in a note somewhere on my computer, but don't worry too much. Not important, right? But that's it. We have a second, and we know roughly how long a second lasts, right? We can say 1/1000, right? And a second has passed. But we have a much more accurate way of doing that. Prior to developing clocks, how did we keep time? Yeah, right? Before there were like mechanical watches, mechanical clocks, right? There were sundials and watching the position of the sun in the sky, right? So we have these sort of reliable clocks, right? We know the sun comes overhead and then it rises, it comes overhead and then it sets, right? And then it does that again in a very, very reliable amount of time, right? So if you're standing outside and you have the sun overhead at noon, right? When will the sun be overhead again? How many days or hours or minutes? How long until the sun comes back overhead again? 24 hours, right? Because the day lasts 24 hours, right? Now, to be clear, is the sun moving? No. What's moving? We're rotating, right? It looks like the sun is moving because we're sort of stuck on Earth, right? But really the Earth is rotating. Okay, excellent. So before we had these mechanical clocks, we had other ways of measuring time, like sundials and just watching the position of the sun in the sky. And long periods of time could be measured by watching things like the phases of the moon, right? We know the moon has like a 28-day cycle, right? Where it goes from a new moon to waxing crescent to full moon to waning crescent back to new moon, right? It has a sort of 28-day cycle. So we measured months with the moon, right? We had the lunar calendar. And we measured things like the year with the position of the sun in the sky, right, at certain times of the year. So we had all these ways of keeping time for thousands of years, right? We now have a much better way of measuring time. Number of times an atom of cesium vibrates per second, we call that a second. All right, so the next one is length, okay? Length is the meter. So our unit for length is the meter, okay? And this is now based on the distance. So we know a couple things now. We know we've learned some things from the late 1800s to now. We learned that light travels at a finite speed, okay? It's 300 million meters per second. That's how fast light travels, okay? What do you know about the speed of light? Tell me something you've heard about the speed of light. I mean, I just told you the speed, but anything else that you know? Can it change? No, it's fixed. It's a constant. Okay, the speed of light cannot change. It's built into the laws of physics. The speed of light does not change. It's 300 million meters per second, no matter what's going on. Okay, so because we know the speed of light, we know that if light travels for a specific. So let me backtrack. What is speed? How do we measure speed? Velocity. In your car when you're driving here, how do you know how fast you're going? You look at your speedometer and it tells you you're driving 65 miles per hour, right? So your velocity, your speed, is distance over time, right? So if we have something that's traveling at a specific speed and it doesn't change, light, 300 million meters per second, yeah? And we let it travel for a specific amount of time, we know how far it's gone, okay? Because velocity is distance over time. If I know the velocity, and I know the amount of time I've let it travel for, I can know how far it's traveled, okay? So it happens that the meter is the distance light travels in 0.0000033 seconds. Yes?
Does it burn a zero when they reach at a certain
How do you mean?
Like, if it goes up to like 100, or like, and then it burns another zero, then it burns another zero, it keeps going, going, going.
Um, no, no, I don't think so. I may be misinterpreting what you're asking, but I don't think
I'm
so.
kind of thinking of it like crypto, but sorry.
Oh, gotcha. So it's 0.0000033 recurrent. Um, but that's the deal, right? Light has a specific speed, right? And the formula for speed is velocity equals distance times time. So if you know the velocity, the speed, if you know the time, then you know how far the light has traveled. So now we have a very super duper accurate way of saying here's how long a meter is, okay? And then we can base all of our meter measurements, meter sticks and all that off of that, okay? So it all has to deal now, like these big measurements, the meter, the second, are all built on small things. The meter's built on how far light travels in a specific time interval, and the second is given by the number of vibrations of a cesium atom. So we use that to measure how long light has traveled for. So we use the second to get us the meter, okay? Time and length, alrighty? There's a lot of interesting stuff about time and length that we can talk about, but I need to move on. If you want to know more, let me know. I'll give you more. The third standard unit is mass. Okay, mass is intrinsic to the thing that's making it, right? So let me read from here first. Mass is measured by the kilogram. Okay. Now here's what's cool. So the way they did this was mass is measured by the kilogram. It's the amount of weight, that amount of water that fits inside of a 1,000 centimeter cube, okay? So a 4-inch by 4-inch or 10 centimeter by 10 centimeter by 10 centimeter cube like that big, holds 1 liter of water, and that 1 liter of water weighs 1 kilogram. Okay, so 1,000 cubic centimeters holds 1 liter of water. That 1 liter of water weighs 1 kilogram. Okay, and that's how we have our units of mass, and our units of volume, spatial volume, cubic centimeters, and our liquid volume, the liter. It's all based off of that. Okay, they're all three together. So we can now safely say things like if 1,000 cubic centimeters, 4-inch by 4-inch by 4-inch cube, holds 1 liter of water, then one of those cubic centimeters will hold 1 milliliter of water. And you know this from medical assisting, right? You know if you draw up 1 cc of liquid into a syringe, you've actually drawn up 1 ml of that liquid, 1 milliliter of that liquid, okay? And so that's the deal. Mass is an amount of matter. This is important. Mass is an amount of matter. Mass is not your weight, okay? Your weight is entirely dependent upon the gravitational field that you're in, yeah? You know that if you accelerate very fast in your car, you feel heavier towards the back of the car, right? You know that sitting here on Earth, you feel a downward force. You're being pulled down by Earth's gravity, right? If you changed the gravity of Earth, making the Earth smaller or bigger, or if you just went very far away from Earth, right? You don't feel that same gravity. You don't feel that you weigh the same, right? Have you ever seen any of the clips of the videos of the astronauts jumping around on the moon? Yeah? Do they look like they're on Earth? No, right? How do they move differently on the moon?
Gravity.
Yeah, no, gravity's why, but what does it look like?
It's like they're like floating.
They're kind of floaty, right? They take a step and they kind of boing and they bounce down to the next step, right? Earth's gravity is about 6 times stronger than the moon's gravity, okay? So, you know, whatever you weigh here on Earth, right? Let's give an example here. So let's see. On the moon, a body may only weigh 27 pounds, even though it would contain, 70 kilograms of matter, okay? 70 kilograms, roughly 150 pounds, right? So you would stand on a scale on the moon, you weigh much less, right? Are you still made of the same stuff? Yeah, here on Earth, you're made of stuff, and up on the moon, you're made of stuff. But you weigh less on the moon, okay? Weight and mass are different things. Weight is what do you weigh in a gravitational field, right? Mass is how much stuff are you made of. Okay, we measure mass in kilograms. We measure weight in pounds. Okay. All right. So the only difference between mass and weight is location. So yeah, here on Earth, though, if I weigh 100 kilograms, right? I have a mass of 100 kilograms. If I step on a scale, that scale is going to show me that I weigh 100 kilograms. Okay, so here on Earth, weight and mass we can sort of interchange them, but they're not. It's not a universal thing. Mass is the same. No matter where you go in the universe, you're going to have the same mass, right? But you will weigh different amounts. Yeah. If you look at the astronauts on the International Space Station, right, they're in free fall. They look floaty inside of their space station, right? Because they're in free fall around the Earth. Okay. Time, distance, mass are 3 units of measure. Every other unit of measure that you know about in the world is derived from these 3, taken from these 3. It's a combination of these 3. It all boils down to these, okay? For example, speed. We talked about speed, right? Speed of your car, right? That is distance over time, right? You're driving 65 miles per hour, yeah? You can boil the hour down to a second and the mile down to what it is in meters, right? Meters per second, okay? So length divided by time is speed. Density of matter, right? Air is, you're more dense than air, right? You know that because you don't float, right? But take a balloon and fill it with helium and it floats, right? Is it anything special about the helium? Is helium intrinsically floaty? No, it's not intrinsically floaty. Helium's just less dense than air, right? If you go jump into the ocean or a swimming pool, you can float, right? Not in all circumstances. Like have you ever sat in the pool and taken a big deep breath of air in, right? Filled your lungs with air. You're making yourself a little less dense when you do that, okay? And you kind of float towards the top of the swimming pool, right? If you blow all your air out, you can sink down to the bottom of the pool, right? You're changing your relative density to the water, right? You're not making yourself more or less floaty. You're just changing your relative density compared to the water, right? Density is mass over volume, mass divided by volume. It's a number of grams of weight per volume of space, right? The more grams of matter that you stuff into a volume of space, the denser that material is going to be, right? Such as you being more dense than the air in the room. Okay. So every other unit that we'll talk about is taken from these 3: time, distance, mass. All right. Those standard units are universal. They apply everywhere in the universe, and these are the base units that we use. The second should work everywhere. The unit of distance should work everywhere, and same with the units of mass. Okay. Next, we learn a lesson from Albert Einstein. Okay, what are you probably heard of him? What's he famous for? E equals MC squared. Enrique, what were you gonna say? Nothing? All right. There's no bad ideas here. So you probably know that Einstein's famous for E equals MC squared equation. I'll hopefully try to help you understand what that means, okay? But he's also famous for his theories of relativity, right? Special relativity, general relativity. You know that Isaac Newton, back in the 1600s, discovered the theory of gravity, right? You probably know about Newton, and he discovers gravity. By the way, they knew that gravity was a thing. They just didn't know how exactly that it worked, right? Newton put equations to gravity, okay? But then you get to 1905, Albert Einstein discovers something called special relativity. Special relativity is all about the speed of light. We know that the speed of light is a constant, right? We know all about that because of Albert Einstein and special relativity in 1905. That is where we got the equation E equals mc squared. Okay, I'll talk more about that in a moment. Fast forward to 1915, Einstein gives us the theory of gravity. Gravity is the warping or bending of space-time. Okay, won't go into that at all. That's not part of our core curriculum, but it is some of the most interesting stuff in all of physics. Special and general relativity, Albert Einstein's, both of his theories. Anyways, from Einstein and his big work he did in physics in the early 1900s, we learned that the universe is a continuum of space and time, okay, or space-time, okay? In space-time, there's only two things. There's matter, which is made of mass, and energy, okay? In fact, Einstein shows us that matter is just a form of energy. That's the equation E equals mc squared. So let me read the equation to you. E is energy, is equal to mass times c squared. We're not going to worry too much about what c squared is, but c is the speed of light, okay? C for constant. Remember, the speed of light doesn't change, okay? So if you ignored the c squared part of that equation, what does it tell you?
Energy equals mass.
Yeah, right? Say it the other way.
Mass equals it.
Yeah, mass equals energy, okay? Every massive thing, every piece of matter can be converted into energy, and enough energy can be converted into mass. But it's not an equal back and forth, okay? Because of the c squared part of it being on the mass side of the formula, small amounts of mass can turn into large amounts of energy. But it takes large amounts of energy to produce small amounts of mass, okay? E equals mc squared. Every mass has an energy, and every energy has a mass equivalent. They are interchangeable things. There's really only one thing in the universe, and it's energy, taking different forms, okay? One of the laws we'll learn is the law of conservation of energy, and this law simply states that energy is not produced or destroyed, but it changes forms. One form that energy can take is mass, okay? This was a huge breakthrough in our understandings of how the world works, right? Energy and mass are really connected, right? Those of you who've watched the Oppenheimer movie, right? That's how the dude and all the other dudes and dudettes figured out how to make atomic bombs, right? They figured out how to take atoms and convert their mass to energy, okay? Making big explosions, right? If you convert mass to energy in the right way, you can release a lot of energy, okay? Our nuclear power plants do this all the time, okay? They convert mass to energy all the time by smashing apart atoms, right? One of the huge tasks in physics right now is to do what's called fusion energy, to take two massive particles and fuse them together, releasing free energy from it, okay? Converting mass to energy, right? This is how the world works. Mass and energy are interchangeable with each other. Okay. That's a really important thing. You'll need to kind of stew on it for a while and think about maybe look at other sources that might give you a little bit of extra insight. But that's the deal, right? Mass and energy are what we have in the universe. Those exist within space-time. All right. Let's now talk about our forces, okay? The forces are, forces move matter, okay? Forces affect matter, right? So we have the first force is gravity, right? Now, let me be clear. These forces are listed in an order. They are listed in order from weakest to strongest, okay? Does it feel like gravity's pretty strong to you? It should, right? You feel like you're being pulled down towards Earth, right? If I wanted to escape Earth's gravity, what do I have to do? Get on a rocket, right? Which takes I don't know if you've ever seen a rocket launch. They take a ton of energy, right? They're hugely energetic things just to move a couple of people up out of Earth's orbit, right? A couple people, some instruments, right? A lot of energy is required to move you out of Earth's orbit, okay? Gravity is the weakest force, okay? Think about it like this, right? You feel like you're attracted pretty strongly to Earth, right? But it takes the entire Earth to hold you down, okay? It's the entire gravity of the entire planet that's pulling on you, okay? It's the weakest force. It can very easily be demonstrated how gravity, how weak gravity is. I mean, all I have to do, I forget if this is magnetic or not, this board. No. Okay. But all I have to do is clip a magnet on right there, right? If I let that magnet just be out in space, it falls, right? Gravity's pulling it down. But that magnetic attraction, the electromagnetic attraction between the magnet and that other piece of metal, right, keeps that magnet from falling, yeah? Electromagnetism is down here. Magnetic phenomenon, which that magnet is a magnetic phenomenon, right? Gravity, so much weaker than that magnet, okay? I mean, you ever taken a balloon and like rubbed it on your hair and created a bunch of static electricity, right? You can take that balloon, stick it to the wall, right? That just little bit of static charge can counteract the pull of gravity, okay? I can do the same thing with like anything, like a paperclip, right? This paperclip will fall in the gravitational field, but it's counteracted by the force of this magnet, right? Not a strong thing, but it's counteracting the entire, think about that, right? This paperclip's being pulled by the entire Earth right now, right? The whole Earth is pulling on the paperclip. And this one little teensy little magnet has the power to counteract the entire Earth's gravitational pull, right? Okay, so gravity's really weak, like billions of times weaker than any of these other forces, okay? It's the weakest force. But gravity's special, okay? Gravity's special in a couple of ways, but one way it's special is gravity is only attractive. There is no, as far as we know, repulsive gravity. Gravity can only attract things, okay? It's only a positive force, okay? All forms of matter attract all other forms of matter, okay? This is why we orbit around the sun. The sun pulls on us, we pull on the sun, right? And we orbit around the sun. Why doesn't the sun orbit around us? Well, for a couple of reasons, but one major reason is we're a lot smaller than the sun, right? We orbit the sun's center of gravity, and the moon orbits our center of gravity, right? Gravity attracts all other forms of matter to each other. It's always an attractive force. The next force down is called the weak nuclear force. Now, you probably never heard about this force except for in this context. The weak nuclear force has to deal with the nucleus of atoms, okay? We're going to do a whole lecture on atoms next time we talk, okay? But you probably know about atoms. You probably have like a toy picture of atoms in your head, right? A dense nucleus with electrons orbiting it, yeah? You may know that in the nucleus of an atom, there are two types of particles. Does anybody know what those are?
Neutrons and protons.
Exactly, right? How are they different?
The protons have a positive charge?
Yeah, positive electric charge, and the neutrons have no electric charge, right? And hence the word neutron, right? Or neutral, right? You may also know that neutrons, which are the neutrally charged stuff, are not, they're not a single thing. They're a composite particle. They're made of protons and electrons, okay? Protons and electrons, positive and negative charged particles, you combine the two and you've got a neutron, okay? The force responsible for controlling how those particles interact with each other and when they radioactively decay, you may have also heard that neutrons are a little unstable and tend to break apart, okay? The force responsible for holding them together, for allowing them to break apart, we call that the weak nuclear force, okay? And that's all you need to know about the weak force. It's not that important for what we do. It works inside of the nucleus. Gravity is a long-range force, right? You know it's long range because we feel the sun's gravity, right? The moon, which is 250,000 miles away from us, right? The moon pulls on our oceans, creating our tides, yeah? You know, the tides come up like meters, like they come up high, right? That's all the moon. That's all the moon yanking on our oceans, okay? Gravity's a long-range force. It extends over astrophysical distances, okay? However, the weak nuclear force, stronger than gravity, billions of times stronger than gravity, but it only works inside of the nucleus, okay? That force drops off rapidly outside of a nucleus of an atom. So we don't feel the weak nuclear force out here, okay? The next force down, electromagnetism. This is the one where we spend the most time on, right? That's why I brought magnets out, right? So the force responsible for the interaction between magnets, the repulsive action, trying to push these two magnets together. They don't want to go together. Why don't these magnets want to go together?
The same.
I'm pushing two north poles or two south poles together, right? I don't know which, but I'm pushing the two poles together and they don't want to go together, right? But if I flip this magnet around, it attracts right to the other one, yeah? That's no surprise. You guys have played with magnets your whole lives, hopefully, right? Even just on your refrigerators, right? Electromagnetism is responsible for that, what magnets do, okay? Electromagnetism is also responsible for lasers and lights and all that, okay? All of the forces that are electrical or magnetic are all part of one thing called electromagnetism, okay? All electric and all magnetic phenomenon, behavior of all magnets and all electric charges. Everything coming out of my screen, all the light coming out of the screen, the electricity powering my screen, the x-rays we make in the x-ray room, all the lights you've ever seen, right? The UV light that's giving you all your sunburns, that's all electromagnetism, okay? And that's what we're going to try to learn more about as we go forward. The last force, oh, and by the way, electromagnetism is also a long-range force. It's long-range like gravity, right? You know that because you can go outside at night and see a bunch of twinkling stars in the sky, right? They're sending their light to you, yeah? Remember I told you last time, the closest star to us, you guys remember how far it is? 4 light years away, right? That's the closest one to you, okay? Remember, a light year is not an amount of time. It sounds like an amount of time, right? Year. A light year is a distance, okay? It's the amount of distance light travels in 1 year. Think about that. The star Alpha Centauri, 4 light years away, emits a photon of light. That photon of light travels through interstellar space for 4 years before reaching us. And that's the closest star to us, okay? We can see light from galaxies that are 13.8 billion light years away. Billions of light years of distance, right? So the point is, electromagnetism is long range, right? We're able to get light from the other side of the universe, right? That's incredible. And that's electromagnetism. So our 2 long range forces are gravity and electromagnetism, okay? That means the only forces that can act on you from outside of your atoms are gravity and electromagnetism.
Crazy. That means like you're seeing the light.
Yeah. At the beginning of the universe.
Before Earth was created.
Yeah. So we can get light, like for example, I don't know how science-minded you guys are and how much science stuff you guys follow, but do you know about the James Webb Space Telescope that just got launched a few months ago? Okay, it's supposed to give us the clearest pictures of the earliest days of our universe. Our universe is 13.8 billion years old. Okay, the James Webb is seeing the galaxies that were created just a few 100,000 years after the birth of the universe. Okay, we can look back to the beginning of the universe because remember, light travels a finite speed, right? So the further out you look and see light from further away, that light takes time to get to you, right? So if you're seeing 13.8 billion light years away, that means that light that you're seeing is from 13.8 billion years ago on that side of the universe, right? You can see back in time when looking out into the universe. Okay, yeah. So you can see things, before our solar system was created. Our solar system's what, 4.6 billion years old, something like that, right? And we can see further than 4.6 billion light years away. Yeah. So that's electromagnetism, long range electromagnetism and gravity. Okay. The last force, remember we're getting stronger as we go down. The last force is called the strong force, or the strong nuclear force. This is your other of the 2 short-range forces. This force only works inside of the nucleus, okay? What do you know, like remember remember the magnets, right? If I take 2 north poles of a magnet and try to push them together, they don't go together, right? As well, if I try to take like 2 positive electric charges and try to push them together, they'll repel each other, right? What we say about electricity and magnetism is like charges, 2 positive charges, so 2 like charges, repel each other. 2 negative charges would repel each other, right? Opposites attract, like charges repel, okay? But you also know that inside, and as you correctly said, right, what's inside of a nucleus of an atom? Yeah, so let's focus on the protons for a minute, right? What did you tell us about protons? Positive electric charge, right? But I just told you there's a bunch of protons inside of the nucleus sitting right next to each other, right? So what should the protons in the nucleus be doing? Repelling each other, meaning that nuclei should not exist, right? But we've got nuclei atoms have nuclei. They have bunches of protons in the nucleus, right? Even like the smallest atoms, like helium, there's two protons sitting right next to each other in the nucleus, right? Protons sit together when they should be repelling each other. So there has to be an explanation for why. The explanation is the strong force, okay? The strong force is stronger, and oh, let me backtrack. What force, which one of these four forces is pushing the two positively charged protons apart? The electromagnetism. That we just said that's a positive electric charge, right? Yeah.
Oh, I think the computer froze.
Okay.
Yeah, should I restart it? And, I don't know.
Let me come take a look.